Now we talk about Pochhammer symbols as we continue with special functions. This may be new to so many people, but by the time this class is over, you'll be very familiar with the whole idea of Pochhammer symbols. Introduction: the Pochhammer symbol is a compact notation used to represent products of consecutive terms. We are used to the idea of factorial already, right? If you have 5 factorial, you just have 5 times 4 times 3 times 2 times 1, or if you like, 1 times 2 times 2 times 3 times 2 times 5. So, but this Pochhammer talks about consecutive terms, not necessarily starting from 1. So, Pochhammer symbols appear extensively in combinatorics, special functions, hypergeometric series, probability theory, mathematical physics, and differential equations. There are two important versions of Pochhammer symbols. You have the rising factorial and the falling factorial. By the way, it's not the regular factorial. So we'll see that now. So rising Pochhammer symbol now. The most common form is the rising factorial, and by definition, that is x sub n equals x. So you start from wherever you're at. Instead of starting from 1, like factorial, you don't start from 1 here. You start from wherever the number you're starting with, and you go as many steps as you have n. So x sub n would then be x times x plus 1 times x plus 2 up to x plus n minus 1 as you go n times like that. So with x sub 0 equals 1, right? As you're going to see soon. So when you have x sub 0, that's 1 already. So this notation is also called the rising factorial, or if you like, call it the ascending factorial, or simply the Pochhammer symbol. So let's see the first few examples. So if you have, of course, we know x sub 0 is 1, x sub 1 is x sub 2 will be x multiplied by x plus 1. So you go 2 steps. X sub 3 is x times x plus 1 times x plus 2, 3 steps. X sub 4 is x into x plus 1 into x plus 2 into x plus 3. So counting from x, you go 4 steps. So consecutively, that's 1, 2, 3, 4 multiplied together. So for instance, if you have to deal with 3 sub 4 as in Pochhammer symbol, 3 sub 4 means start from 3 and keep multiplying until you go 4 steps. That's 3 times 4 times 5 times 6. That's 3, number 1, 4, number 2, 5, number 3, 6, number 4. That's 3 times 4 times 5 times 6. Therefore, 3 sub 4 is on 360, like that. Then we have the fractional example. So if you have fractional example, just keep increasing it by 1, 2, right? So 1 over 2 sub 3, that's half multiplied by half plus 1, that's 3 over 2. Multiply by half plus 2, that's 5 over 2. And then you can multiply everything together. You have 15 over 8 now. So compute numerator and denominator separately. That's 1 times 3 times 4, that's 15. All over 2 raised by 3, that's 8. So it means half sub 3 is 15 over 8. That's the simple idea of Pochhammer symbols. Now, why it is called a rising factorial? The factors increase upwards. So you have x plus 1, x plus 2, x plus 7. Hence the name rising factorial. So in essence, if we need to have 10 sub 5, so we are saying that should be 10 times 11 times 12 times 13 times 14. That's 1, 2, 3, 4, 5, like that. So, and what does that give us? So we have, let me see if uh, Google can do it directly. 10 sub 5. Let's hope it recognizes the idea. So that's 10 sub 5. Does it see that? Pochhammer symbol. Maybe it does. I'm not sure. Uh, I'm not sure if this is Pochhammer though. But it's okay. Let's just do the normal thing. 10 sub 5 means we have 10 multiplied by 11, multiplied by 12, multiplied by 13. That's 4 now. Multiplied by 14. And then we get the result. That's 240, 240, 240, 240. So that's what that is about. 240, 240. So that's what we get. 240,240. That's 10 sub 5 for rising factorial. So let's talk about the other part, which is about falling factorial. So that's just the reverse. Another important version is the falling factorial definition. You have x power, instead of n being down, so you have x power n under. So you have x into x minus 1, x minus 2, until you get to the number of steps indicated. Whereas x power 0 sub is 1, just like x x of 0 for rising is also 1. So example now, if you have 7, 4 under 4 underline like that, so the expansion will just be, so just go 4 steps from 7, starting from 7, go 4 steps down. So 7 times 6 times 5 times 4. That's like 20 times 4, 20, which is 840. So therefore, 7, 4 like that is 840. So now, well, I'll just go back and do what I did before with 10, 5. Okay. So for 10, 5, now maybe I now have 10, 5 like this. So that means I have 10 times 9 times 8 times 7 times 6. Okay. So as unlike factorial, which start from 1, this one starts from any number you start with and goes up or down, depending on whether you're dealing with rising or falling factorial. So of course, if you like, this is like 10 times 9 is 90. Okay. 10 times 9 is 90. 8 times 7 is 56. And then you have 6. Then I can try again. 90 times 6 is 540 times 56. I'm just trying to do it my own way. So that's 540 times 56. 6 times 0 is 0. 6 times 4 is 24. I have 2 held. 6 times 5 is 30. That's 32. Then 5 times 0 is 0. 5 times 4 is 20. I hold 2. 5 times 5 is 25. That's 27. So I have 0, 4, 2, 0, 3. That's 30240. That's 30,240. Okay. So I could have done the same thing here too. This is let me see the ones that are easy to multiply. Um let me see. Okay. Of course, this is okay. 10 times 13 is 130. Then 11 times 12. 11 times 12 is 132. Okay. And this is now 14 here. This is 14. So what else can I do? Um, so okay, I can check 130 times 132 times 14. 130 times 132 times 14. 130, 130 times 132 times 14. Same, 240, 240. So that's correct there. Okay, so this is, but let's check this other one too. 30,240, that's 10 times 9 times 8 times 6. 10 times 9 times 8 times 6. 10 times 9 times 8 times 7 times 6. So that's 30,240, correct. So we move on. Comparison between rising and falling factorials. So for rising factorial, we have x sub n, which is x into x plus 1 into x plus 2, and it keeps going and stops at the number indicated. For falling factorial, you have xn underscore. So you have x into x minus 1, x minus 2, and so on. Now, relation to ordinary factorials. Now, we know the ordinary factorials. That's 5 factorial is 5 times 4 all the way down to 1. So for positive integers, you have x sub n now to be, that'll be x plus n minus 1 factorial all over x minus 1 factorial, while this other one now, xn underscore, is x factorial over x minus n factorial. So we can, okay, we have an example here. Excellent. So we have an example here. 5 sub 3 for rising factorial, that's normally 5 times 4 times 3, right? 5 times 4 times 3, that's 20 times 3, which is 60. So is it 60? 5 times 4, 20 times 3, 210. Okay, good. So using the factorial formula, so that will be 5 plus 3 minus 1 all over 5 minus 1. So 5 plus 3 minus 1 is 7 factorial. 5 minus 1 is 4 factorial. So that's 50, 40 over 24. If you like, 7, that will be 7 times 6 times 5. So 4 factorial cancels 4 factorial. So you have 210 at the end of the day, right? So that works. So that actually works. So so we have that connection between rising and falling factorials with respect to the regular factorials like that. Okay, so let's check for falling factorial now. So let me still do 5, 3. Okay, let's do 5, 3. So we have 5, 3 like that. So of course we know this should be 5 times 4 times 3, and that is simply 60. That's for falling factorial. So, but 5, 3 is actually going to be uh 5 factorial all over, what's the formula now? X factorial, right? All over x minus n factorial. So that's all over x minus n factorial. That's 5 minus 3 factorial. So that's 5 factorial over 2 factorial. That's 5 times 3. 5 times 4 times 3 times 2 factorial. 2 factorial cancels out. So that goes. So that's simply 60 also. So we are good to go like that. Okay. So done, done, done. So connection with the gamma function now. What's the connection of Pochhammer symbols with gamma function? The Pochhammer symbol can be extended to non-integer values using the gamma function. Important identity is that x sub n is gamma x plus n all over gamma x. Of course, that makes sense because that connects with the idea we came up with here. So because x plus n minus 1 factorial is the same thing as gamma x plus n, then x minus 1 factorial is the same thing as gamma x. So that still makes sense. So x sub n is gamma x plus n over gamma x. This allows the definition to work for fractions. So this can then work for fractions, real numbers, and complex numbers. So we can then find maybe half 3, we can do half 3, and then we do the whole gamma thing and keep going. Then gamma function example in that case now, we have all of this. So you want to compute half sub 4. Using the gamma identity now, that will simply be gamma x plus n. That'll be half plus 4, which is gamma 9 over 2. Then all over gamma half, right? So all over gamma half, that's gamma x. So we can then do gamma half, of course, we know that's root pi over 2. So gamma n over 2 is then 7,531. All right. Then 2 raised power 4, because, you have this, you have so in fact maybe root pi is going to cancel root pi. Root pi will cancel root pi, so we just have 75321, and then 7 times 5 35, 35 times 3 105, 2 raised power 4 is 16 root pi. So that just goes like that. So then we have okay, all of this is coming from 9 over 2, right? That's 7 over 2, gamma 7 over 2. We have that. Then for 7 over 2, gamma 7 over 2, that's 5 over 2, gamma 5 over 2. From gamma 5 over 2, you have 3 over 2, gamma 3 over 2. From gamma 3 over 2, we now have half, gamma half. So gamma half is root pi, and that's where we have this all liberated to be 105 over 16, because root pi will cancel root pi in both cases. At the top and bottom, you have root pi, root pi. So this cancel out. So you just have this part left. Okay, then we have the recurrence relation. So the rising factorial satisfies that x sub n plus 1 is the same thing as x plus n into x sub n, like that. So because, of course, from what we've done here, so it's just all a matter of, xn plus 1. This will just be x plus n plus 1 all over gamma x, like that. So gamma x plus n, so that's just x plus n over times x of n. So this allows recursive computation, so we can keep doing recursive computation. So this tells us that x sub 3 will be x plus 3, then x sub 2. No, x sub 2, x plus 2, x sub 2, like that. So this will now allow for recursive computation. Then we have the polynomial nature of this now. So for fixed n, the expression x of n is a polynomial of degree n. So polynomial expansion example, for instance, so you have x sub 3. So you start with x sub 3, which is x into x plus 1 into x plus 2. If you multiply that out, x plus 1 times x plus 2 is x squared plus 3x plus 2. Multiply by x, you have x sub 3 is now x cubed plus 3x squared plus 2x. So it's, but if you have x, not a number now, it basically has a polynomial nature. Then we have connection with binomial coefficients. So falling factorials appear naturally in combinations. For instance, x combination n is the same thing as x n underscore all over n factorial, basically. So this generalizes binomial coefficient to non-integer values. So the beautiful thing about this is that we can use it for non-integer values like fractions, negative numbers, and all that. Then we have generalized binomial theorem now. So for arbitrary alpha, 1 plus t all raised power alpha is simply summation from n equals 0 to infinity of a combination n t raised power n. And using following factorials now, a combination n is a n underscore all over n factorial like that. Then we have hypergeometric functions, which we found to be very important when we dealt with the introduction of special functions. So hypergeometric function unifies so many functions. Now, we know already that special functions arise when we get to solve differential equations and elementary functions like polynomials, logarithms, exponents, and all trigonometric expressions cannot suffice. Then we go for special functions like beta, gamma, Bessel, Legendre, Laguerre, Hermite, and so on and so forth. So Pochhammer symbols are central in hypergeometric series. So by definition, we have P F sub Q of A1 up to AP, semicolon B1 up to BQ, semicolon Z now. It's simply the same thing as summation from n equals 0 to infinity of A1 sub n. Of course, we already know that'll be A1 times A2 all the way down to n, all the way up to n if you like, to n steps. Then, and all of that goes to, then you have A1 sub n multiplying all the way to APN. So all over B1n up to BQn, and then you have Z raised power n over n factorial generally. So let's take an example of that. Oh, okay, maybe not an example. Exponential function as a hypergeometric function. So the exponential function satisfies e raised power 0, which is 0f0, all right? Then dash dash z, because e raised power z is simply this part now, simply this part, because all of these other ones are just 0, 0. So you just have summation from n equals 0 to infinity of 0 raised power n factorial. That's what the exponential function looks like in terms of hypergeometric function. Then we have the differentiation formula. The derivative of a rising factorial is simply this. d dx of x sub n is simply x sub n multiplied by summation from k equals 0 to n minus 1 over 1 over x plus k, like that. Then, yep, so we have that. Then we have Sterling numbers connection. So the Pochhammer symbol connects ordinary powers and factorials, right? So expansion into ordinary powers now. X sub n is now summation from k equals 0 to n of s of n comma k x raised power k. So where s of n comma k are Sterling numbers of the first kind. So you have that Pochhammer symbols connected to Sterling numbers. Then we have reverse expansion. Ordinary powers can be written using following factorials. So x raised power n can be written as the summation from k equals 0 to n of Sn comma k x k underscore, where Sn comma k are Sterling numbers of the second kind. And then we have generating function. An important generating function will be summation from n equals 0 to infinity. Then we have the rising factorial here of x sub n, t raised power n over n factorial, which is 1 minus t raised power minus x, like that. This is an important generating function. Then an example of that will be this now. So you have 1 minus t raised power minus 2. Using the generating function, that's simply summation from n equals 0 to infinity of 2 sub n t raised power n over n factorial. So to compute the coefficients now, if you start from 0, when n is 0, you have 2 sub 0, which is simply 1. Anything sub 0 is 1. Then you then have 2 sub 1, which is 2. 2 sub 2, that's 2 times 3, which is 6. Then then 2 sub 2 is 2 times 3, 6. 2 sub 3 is 2 times 3 times 4, which is 24. Right? So you keep going like that. And as you keep going, of course, at n equals 0, this is simply t raised by 0, 1 over 0 factorial. That's also 1. So that's why the first term is a constant. The next one, t raised by 1 over 1 factorial. That's why you have t here. Then you have t squared now. So that's t raised by 2. Uh, you know, um, so you have 2 raised power 2 over 2 factorial. That's 6 over 2, which is 3. And here you have 24 over 6 factorial, which is 4. That's the 1 minus 2 raised power minus 2 is 1 plus 2t plus 3t squared plus 4t cubed. Using normal binomial expansion, you still get the same thing, by the way. Okay? So we just see how this is connected to the idea of Pochhammer symbols. Then we have combinatorial interpretation. So the following factorial xk underscore is x factorial over x minus k factorial. Counts the number of ordered selections of k objects from x objects. So that's like n combination k, that's x combination k rather, because it's the very definition of x Oh, X permutation K, it is number of ordered selection. That's arrangement now, not selection, arrangement, right? So it's more like X permutation K, not combination, X permutation K. Then we have Python codes for this now. So for rising factorial, you want to, so you define a function, rising factorial, X, and the result is one. I mean, that's initialization. So for K in range N, so if you fix whatever your N is now, like here now, X is 3 and you have 4. So that's 3 times 4 times 5 times 6. 3 times 4 times 5 times 6. That's 360, right? 3 times 4 is 12. 12 times 5 is 60. 60 times 4, no, 3 times 4, 12, right? 12 times 5, 60. 60 times 6, 360. Yeah, that's exactly what you have right here. So that's for rising factorial for 3 sub 4 now. 3 times 4 times 5 times 6. So you go 4 steps starting from 3. Then you have the symbolic expansion. So we can do the symbolic expansion and it gives us exactly the same idea. Okay. Then so that's still 360 using the idea of rising factor. Here, what we defined was a function, a Python function, but here we use the actual rising factorial uh, um, uh, you know, function to run it directly and we get the same result. And then we can have it as a form of expansion. So you can do symbolic expansion in Python. So from SymPy, you can import symbols, and when you expand, you have X symbols. So you create your symbols. I did this under scientific competition with Python, talking about symbolic Python, SymPy. So the expression will now be rising factorial x comma 4. So you now expand the expression x raised by 4. So imagine we take it to like 12. So we're going to have a very lengthy expression. So you see it's going all the way like that, starting from power 12. So let's make it something that can be accommodated in one screen. Say 8. Can 8 come in here? Yeah, 8 can do. So maybe I can go 9 even. That's rising factorial for x sub 9, So that's x into x plus 1 into x plus 2 into x plus 3, and you keep going like that. So this is what you get in this case. So you can also verify the gamma identity numerically. So imagine from SymPy you import gamma and rational. So x rational, that's half, right? That's half. So and n, take n to be 4. So for rising factorial now you now have half 4. That's 1 over 2 times 3 over 2 times 5 over 2 times 7 over 2. We did something like that before. We go 105 over 16. So if you do that's for the left hand side now. If you now do right hand side to be gamma x plus n over gamma x, which is a definition for the same expression, and x is already known for then n is known. So if you check the two out, you discover you get the same 105 over 16 like that. So let's talk about applications of Pochhammer symbols. So in combinatorics, Pochhammer symbols are used in permutations, counting problems, and generating functions. In mathematical physics, they are used in quantum mechanics, perturbation theory, wave equations. In special functions, they are used in hypergeometric functions, Bessel functions, and orthogonal polynomials. In probability theory, they are used in factorial moments, beta distributions, and of course in negative binomial distributions. So there are some important identities we need to pay attention to. So we have a multiplication identity that x sub m plus n is the same thing as x sub m into x plus m sub n, like that. And then reflection, reflection type identity, here we see that minus x sub n is the same thing as minus 1 raised power n x. So the rising factorial here is equal to minus 1 raised power n times the falling factorial. So we also have the ratio identity that x sub n plus 1 over x sub n is the same thing as x plus n, like that. So these are very powerful identities that can be helpful for us to work with. Then we have some complex extensions. So the Pochhammer symbol extends naturally to complex numbers. So you have a sub z equals gamma a plus z over gamma a. So where z may be complex, in this case, z may be complex. So gamma a plus z. So 4.19 tells us about asymptotic behavior. Asymptotic behavior for large n, right? X of the rising factorial is approximately the same thing as n raised power x times n factorial. So this follows from Sterling's approximation. So it follows from Sterling's approximation. So, um, and then we have the summary table for all of that. So the if you look at the concept and the formula, rising factorial, that's x sub n, that's x into x plus 1, all the way down to x plus n minus 1. Falling factorial, xn underscore, that's x into x minus 1, all the way to x minus n plus 1. Then you have gamma relation, that's x sub n, which is gamma x plus n over gamma x. Then binomial coefficient x combination n is the same thing as the rising factorial of xn, that's xn underscore over n factorial. Then we have generating function, summation x sub n, that's rising factorial multiplied by tn over n factorial, that's 1 minus 2 raised per minus x. Then hypergeometric coefficient uses a sub n, same thing, but hypergeometric uses a sub n. The final intuition we want to get from all of this is that the Pochhammer symbol is a generalized factorial. It is ordinary factorial start from 1, 1, 2, 3, but Pochhammer symbol start from an arbitrary value that you start from. Okay, so this simple idea becomes fundamental throughout advanced mathematics. So we have practice problems here. Okay, let me show them in, say, fives. So 4 sub 5, I think, I think I even did that before now. Compute 3 over 2 sub 4, that's 3 over 2 times 5 over 2 times 7 over 2 times 9 over 2. Then expand x sub 5 completely as polynomial. So this is going to be a polynomial of degree 5. Then compute 9, 3, that's 9 times 8 times 7. Then compute 12, 5 underscore, that's 12 times 11 times 10 times 9 times 8, like that. Then from 6 to 10 now. Can we see all of that? I think we can. 6 to 10. So you want to show that x of 2 is x squared plus x. Of course, this is x times x plus 1. So that's x squared plus x easily. Verify the identity that x of 3 is x plus 2 factorial over x minus 1 factorial. Of course, that is what it will be. Then that's for x equals 6. Then compute 7 sub 0, which is that's simply 1, and explain why this value is defined that way. Okay. Um, so evaluate 5 sub 6 over 5 sub 5. Yeah, I think this should simply be 5, right? Because that's 5, so 5, 6, 7, 8, 9, 10. Then 5, 6, 7, 8, 9. So the answer is going to be 10, right? So simplify this. That's possible. Then we have 11 to 15 now. 11 to 15. Write x sub 4 using a following factorial. Expand the following factorial this as a polynomial. Verify using gamma functions that 2 sub 5 is gamma 7 over gamma 2. Compute minus 3 sub 4. Show that minus x sub 3 is the same thing as that. All of this can be shown. Then we have 16 to 20 finally. 16 to 20. So we have 16 to 20. Compute the coefficient of t cubed in the series expansion of y minus series for minus 5 using Pochhammer symbols. Use the generating function this to write the first four non-zero terms of minus series for minus 4. Compute this. Prove the recurrence relation this. Write a Python function that computes the following factorial xn raised power minus 1. Okay, so let's go ahead and solve two problems. So, yeah, so let's go ahead and take care of some business here. So we are dealing with problems 3 and 17. So problem 3 here is about expanding x raised to power 5 completely as a polynomial in x, and 17 is about using the generating function to write the first four non-zero terms of this. So let's go for that, shall we? So we start with problem 3. So problem 3. So expand x sub 5 completely as a polynomial, in X. Okay, that's what we want to do. So the solution is this. So we know X sub 5 already is X into X plus 1, X plus 2, X plus 3, and X plus 4. So you keep going until you get to a step short of 5. So that's 1, 2, 3, 4, 5. That's the concept. So with that in place now, we start multiplying. So we can do this. This is X into. Okay, let's do the multiplication by grouping. So let's do this and this separately. So we have X, we have, so X sub 5 now, rising factorial. So that's X into, to expand this now, we just say X, that's X times X, X squared, plus X plus 2X, that's plus 3X right there. Then 1 times 2 is 2, straight up. Then here, X times X is X squared again. 3X, 4X, that's 7X. Then 3 times 12 times 4 is 12. So easy peasy, we have that. Then we can go step by step again. So we have X into, so we can then take care of all of this. So that's x squared times x squared, that's x raised to power 4, x squared times 7, x, that's 7, x raised to power 3 plus 12x squared, that's this x squared multiplying through. Then 3x times x squared, that is 3x cubed. Let me arrange it for easy addition later. 3x times 7x is 21x squared. 3x times 12x is 36x, like this. Then now 2 goes over, 2 times x squared, that's 2x squared. 2 times 7x, that's 14x. 2 times 12, that's 24. So we can tidy up all of this. So that tells us that x sub 5 is equal to x into x raised to power 4 plus 10x cubed. That's this 2 now. Then 12 plus 21, that's 33 plus 2. That's 35x squared. Then 36 plus 14 is 50x, then plus 24. So yeah, we have all of that. X raised to power 4, 10x cubed, 35x squared plus 50x plus 24. So we have one last step to go. The last step now is just multiply through by x. So x sub 5 finally is then x raised to power 5 plus 10x raised to power 4 plus 35x cubed plus 50x squared plus 24x. So that's how that goes. Okay, so that's problem 3, right? The problem 17. Problem 17. So it says to use the generating function, use the generating function summation from n equals 0 to infinity x sub n t raised to power n over n factorial, that which is to be 1 minus t raised to power minus x, to write the first four non-zero terms of 1 minus t raised to power minus 4. So what do we do? So we have the generating function right here. Okay, I want to write the first four non-zero terms of 1 minus t raised to power minus 4. Of course, using binomial expansion, we can get that, but let's follow the rule, what we've been told to do. So, solution, solution. So we set x equals 4, right? So x is equal to 4, because this is a general expression, but then we are talking about minus 4 here. So x is equal to 4 automatically. So x is 4, right? We set x equals 4 in the generating function, in the generating function. So we have 1 minus t raised by minus 4 to be summation from n equals 0 to infinity for x here. That's 4 sub n t raised by n over n factorial. So we have that. This is infinity, right? So we then say for n equals 0, for n equals 0, we have 4 sub 0. That's simply 1. Okay. And of course, that's then for this other side now we have t raised by 0 over 0 factorial. That's 1 over 1, which is 1. So we have this part and this part. Then we go for n equals 1. For n equals 1, we have 4, 1, which is simply 4. And then that's t1 over 1 factorial. That is simply t over 1, which is t. So we have 4 here and we have t here. Then next, for n equals 2, the first four terms. So 0 is 1, 1 is 2, 2 is 3. For n equals 2, we have 4 sub 2, which is simply 4 times 5, and that is 20. So on the other side, we have t raised by 2 all over 2 factorial. That is t raised by 2 all over 2. So we have 20 here, and we have t raised by 2 all over 2. So lastly, that's the fourth term now. For n equals 3, so we have 4 rising factorial 3. That's 4 times 5 times 6, which is equal to 20 times 6, which is 120. And for the other side, we have t raised by 3 over 3 factorial. That is t raised by 3 all over 6. So we put everything together. So substituting into the series. So to the series, we have 1 minus t raised by minus 4 to be the first thing. So we have 1 here, 1 here. That's 1 into 1. So we have 1. We have 1 into 1. Next, we have 4 times t. So we have 4 into t. Next, we have 20 into t squared over 2. Okay, that's 20 into t squared over 2. And lastly, we have 120. This 120 into t cube over 6. So 120 into t cube over 6 plus all the other terms. So here we have 1 times 1 is 1, 4t. Then 2 here, that's 10. So we have plus 10 t squared. 6 here is 1, 6 here is 20. That's plus 20 t cube plus all of that. And that's what we have there. And we're good to go. So it's all done. And with that, we come to the end of this interesting video on Pochhammer symbols. So I'll flash the questions once more, and then you try your hands on them. So let's go in fives like before. So we have, okay, well, 1 to 6 here. I better still practice problems, right? 1 to 5, 6 to 10, 6 to 10, 6 to 10, and then 11 to 15. 11 to 15, then 16, 16 to 20, 16 to 20, like that. And that's it for this video. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, what exactly are you waiting for? Why not go ahead and subscribe right now? Hit the notification bell so you can so you can always go you can always get subscribe, right? And hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel by clicking on join. That gives you special privileges that you find out when you click. Then ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.